So York actually has a really long history of atmospheric chemistry, which is part of what my discipline is. There's been an atmospheric chemistry program here for decades, and ever since I was a graduate student, I was waiting for those atmospheric chemists to retire so that I could come and work here. And so as of this year, I finally get to come and work at York, which is very exciting. So I'm going to be talking to you today about some of the research that goes on in my group, where we use ice cores to understand pollutant transport. And hopefully we'll get to understand a little bit about how chemicals get from our frying pans into polar bears. Okay, so environmental chemistry isn't something that a lot of people are familiar with. Essentially, it's a very applied chemistry, obviously, and this is a lot of the types of things that we do in environmental chemistry. So as Allison mentioned, a lot of what I do is really analysis-based. So we try to develop methods so that we can better measure pollution in the environment, which is a challenge because those levels are quite low. The environment itself is pretty complicated. There's a lot of other things out there besides the chemicals that we're trying to measure. And we really want to do targeted measurements to better understand the chemistry that leads to climate change, that leads to poor air quality, and that leads to pollutants being transported all around the globe. Okay, so I'm going to talk to you about some pollutant transport. I'll be talking about two classes of compounds. The first are the non-stick compounds. In our frying pans and various other things, we call them the polyfluoroalkyl substances, or PFAS for short. Now, I'm not going to show you too many chemical structures in this presentation, I promise, because the number one response I get when I tell people I'm a chemistry professor is, "Ooh, I hated chemistry." So there's not going to be not too much actual chemistry. We're going to talk mostly about the applications. So this is one of the poster molecules for the PFAS class. This one's PFOS. Okay, the other compounds I'm going to talk about are flame retardants. So these are added to our commercial products to make them not spontaneously combust, essentially. The class I'll be talking about are organophosphate esters, and they look something like this. So one of the thing that's common to these two classes of chemicals is that they are produced exclusively by us for use in commercial products. So we don't find these naturally in the environment. Everything that's there is because we have used it and we've put it there. Okay, so why do we care about Interesting. Okay. So why do we care about these compounds? The first reason, of course, is because they can be toxic. So it's actually quite challenging to assess toxicity for these types of compounds because we're exposed. Every one of us has PFOS in our blood, but it's at very low levels. So what impact does that PFOS that we've had in our bodies for our whole lives have on us? It's pretty hard to say. There are so many confounding factors. How do you isolate the effects that PFOS has and from everything else? So that's pretty challenging. But there is some evidence from laboratory studies, from animal models, that suggests that these are potential carcinogens, and we know that they are endocrine disruptors. So there's been lots in the news about endocrine disruptors recently. These compounds that we're talking about fall into that category. They're also persistent. So this presents a problem. We're not very good as humans at the precautionary principle of preventing pollution until we know there's a definitive problem. But the issue when we're looking at persistent compounds is that we can discover there's a problem, and by then the environment is irreversibly contaminated. So we can't go back to a pristine environment and prevent that harm from happening. A lot of these compounds are also bioaccumulative. So that means species at the top of the food chain are getting a much higher dose than species at the bottom. So it's leading to accumulation through the food chain. And what I'll be talking about a lot today is that they undergo long-range transport. So we're using these molecules. We use them in our everyday lives. There's many of them here in this room. And they end up in pristine environments where they've never been used. So this long-range transport means we're contaminating the entire world with all of our commercial products. Okay, so where do we find them? I've alluded to some of this already. The perfluorinated compounds are non-stick. So we find them in our frying pans, Teflon frying pans, Scotch Guard, basically anything you use to make sure that you don't have to clean too much. That's where we find them. Gore-Tex, before I lived here, I lived in Newfoundland, and Gore-Tex was my best friend. But it does contain these perfluorinated alkyl substances. You'll also find them in food paper packaging. So your fast food wrappers, you don't want that grease to seep through and end up on your hands. That's perfluorinated, these perfluoroalkyl substances. Microwave popcorn bags are loaded with them. So I recommend not licking the inside of the bag. Someone once told me they did that. I was horrified. So don't lick it. I've alluded to this already. Our flame retardants we find in soft fabrics. So your couch is loaded with them. Your TV, they're found in electronics. And the reason that they're there is actually because of legislation in California. This is the primary reason. California had a regulation that the commercial products had to withstand a flame. So in order to withstand this flame, they had to load them up with these flame retardants. And so because California had this regulation, everybody got flame retardant compounds. Now there is a lot of debate about whether these flame retardants actually help us in any way. Do they actually prevent deaths from fire? Well, there's a correlation with increased use of flame retardants and decreased death by fire, but that correlation also coincides with decrease of smoking. So there's a lot of evidence suggesting that it's actually lack of smoking that's causing this supposed benefit from flame retardants. But that's a whole other story. All right, so how do they get into the environment? Basically through us using them. So when we wash our Gore-Tex clothes or our Teflon-coated Dockers, some of it will enter into the environment. When we use things, they can abrade, we get wear and tear. Household dust is loaded with these types of compounds, so it can end up in the environment that way. And of course, once we're done with things, we throw them in the trash. They end up in a landfill or they're burned. Either way, you end up with contaminants entering into the environment. Okay, so we get them into the environment. This is all pretty local so far, but how do they actually get to the Arctic? So there's two possible ways this can happen depending on the chemical properties of the compounds that we're looking at. So if we have something that is, does this work? Yeah, okay. So if we have something that where the chemical properties suggest it could enter into the atmosphere, where it's volatile, then it can volatilize from down here where we're using it, where it's warmer. So it's more likely to enter the atmosphere. It travels on prevailing winds, ends up in the Arctic where it's much colder, and is deposited there. Another way we can have transport, if we have compounds that are water soluble that prefer to be in water, they can actually be transported on the ocean currents, which will take them from mid-latitudes down here, and they can end up in the Arctic up here. So this process, as we know, things move through air much faster than they move through water, so this process is quite quick. We can see time response weeks to a year, and this is more like on the order of decades. Okay, so why do we care about the Arctic? Well, obviously, it's a pristine environment. As I've already mentioned, this is a completely unpolluted area, and what we're obviously, as good stewards of the world, we hope that we will not leave the Arctic as a dump, essentially. So this is a quote that I like from Barry Lopez's Arctic Dreams. With the last animal eating garbage and living on the last scrap of land, his mate dead, would he still forgive you? So of course, altruistically, we would like to preserve the pristine environment of the Arctic. More selfishly, this is very sensitive. Okay. Anyway. More selfishly, we also are concerned about the Arctic because it has a very long food chain. So polar bears and other apex predators end up with really, really elevated concentrations of these contaminants in their bodies. And that's much more so than apex predators in other areas. So in a temperate region, the apex predator is not going to have as many levels of the food web to accumulate these compounds. And of course, when we are talking about the Arctic, we have humans that live in the Arctic that eat some of these apex predators. Northern peoples, some of their traditional foods include seal, and what's not shown on here is beluga. So a lot of northern peoples eat muktuk as a traditional food, and that's beluga blubber that's laden with contaminants. And something that's often ignored is that the very top of the food chain is actually nursing babies. So those babies are getting an additional dose of contaminants from their mother's milk. So this is a huge issue for northern peoples, and it's an issue of social justice as well, because these people aren't really using the chemicals, but they're bearing a lot of the burden. So a lot of contaminants research and long-range transport to the Arctic is done in Canada for these reasons. Okay, so ultimately the question I want to answer is how do pollutants reach the Arctic? Now this is a big and complicated question, so I'll try to break it down and make it a little simpler to answer. Because ideally, if I was, as a scientist, if I wanted to study this, I'd say, great, if I want something to reach the environment, I'm going to release a whole bunch of pollutants and then go to the Arctic and see what I can measure, which of course is totally unethical, although people did used to do that kind of thing in the 70s, but we're not allowed to do that anymore. So what we can maybe do then is use some of the same types of techniques and measure in the Arctic, but use those measurements to understand how our known production changes and regulations affect Arctic pollution. So we've actually done sort of inadvertent experiments where we've changed production of different contaminants, and we can use that information to look at how the Arctic has responded. And we can simplify this even further by saying, can we measure a temporal record of pollutant transport to the Arctic so that we can use that temporal record, compare to production changes and regulations, and see if we can understand what's happening? Okay, so how do we actually measure a temporal record? So for a long time, actually, the way that we did this was by going up and making measurements every year. So the types of measurements that people made were, this is an air sampler. So there's an air sampling station up at Alert. There's another one at Eureka, which has been in the news recently because it was almost shut down again. But there is a continuous monitoring station at Alert, which is at the northern tip of Ellesmere Island. So these samples have to be collected continuously to generate data that we can go back in time and look at any kind of trends. Similarly, we can harvest biological samples every year, and so this is done in collaboration with the northern peoples. So they're harvesting these animals for food, and as scientists, we can take portions of those animals and archive them and use them to understand pollutant transport. So this is continuous collection of multiple samples. This requires a lot of work. More recently, what we have been trying to do is collect a single sample that contains information about past pollution. So our time capsule. And ice cores are a great time capsule. And they're so useful, they operate something like tree rings. So we know we can count in and we can figure out how old that tree was when it first grew. In the same kind of way, ice cores or ice caps, snow falls every year and it remains relatively undisturbed, and it forms these layers that are preserved through time, and we can use those layers to figure out what was deposited in the Arctic many, many years ago. So we have decreasing age with depth, or increasing age with depth, sorry. And the other reason that ice cores are quite simple, obviously we can't use tree rings in the Arctic, but there are other types of samples that provide this kind of time record, sediment cores, sediment deposited in some of the same way. Ice cores are a little bit simpler because there's only one source. We don't have to worry about biological activity interfering with our measurements. So ice caps tend to be high elevation. The one we're looking at is about 2 kilometers above sea level. We don't really have much going on there in the way of, well, there's really no biological activity up there. And all of our sole source is snow. So if we were looking at a temporal record in seals, for example, we'd have a whole bunch of confounding factors because the seals, they breathe, they eat different things, they live in water. There's many, many different sources that could be contributing to pollution. For the ice core, it's a little bit simpler. Our only input is from the air. Okay, so we're going to collect our samples. Our sampling site is up there. Up here. That's Devon Island. It's about 75 degrees north. It's an uninhabited island. It's not. There's no permanent settlements there. There are seasonal settlements of biologists who come to look at birds on the other side of the island. But the ice cap is over here on the east side, and there's nothing going on there. All right. So how do we get there? If you want to go to the Arctic, first you have to get to Ottawa. Then you can fly. Yeah, I know. Then you fly in a commercial plane, which takes you up to, this is Cornwallis Island, and there's a settlement there called Resolute Bay. And there's some government bases there, and that's where we base our research out of. That's where, well, basically all Arctic research is based out of Resolute Bay. So we can get there on a commercial jet. Then we have to hire our own little plane, and it will take us wherever we want to go. So we fly, in this case, to Devon Island, ice cap, and where we can do our sampling. So it's a pretty luxurious ride. I went on one of these sampling trips about a decade ago now, and this was the view from my seat. And it's also not heated, which adds for that's extra excitement because it was minus 25 when we were doing our sampling in May. But the view from outside the plane is pretty nice. So this is Devon Island, and I've got a shot here from also this is Ellesmere Island. So it's obviously spectacular scenery up there. Okay, so we arrive at the ice cap, and this is the airport. Those garbage bags are full of snow. That's how the plane knows where to land. It's very high tech. But our little planes that we rent have skis, so it's pretty exciting taking off in a plane that's wearing skis. But these guys these Arctic pilots are amazing. They're actually the ones who, if there's a rescue that's needed anywhere in the Arctic, sometimes in the Antarctic, these guys are called in. They're amazing. So we were in good hands. Okay, so how do we actually collect our samples? We use something called an ice auger. So it's basically a really big drill, and the drill bit is about this big around, and we drill it into the ice, and we pull up sections of the ice cap. So this is Alison Crisadiello. She's our glaciologist. I'm not allowed to do this. She's actually the manager of the I Score facility that's hosted out of the University of Alberta, so she's amazing, and she collects our ice cores for us. So this is what the drill bit looks like. It's 9 inches in diameter. So you push this into the ice, and you can pull out segments of the ice cap. And what we end up with are sections that are about 1 meter long, and they very carefully measure and archive and provide all the information that's required so that when we get this back to lower latitudes, we can analyze these and know exactly what was found. Occasionally we lose one of the segments. Sometimes that happens. But key thing to notice here, she's wearing lab gloves. So we have to be really, really careful when we go up and do this type of work because our commercial products that we may inadvertently bring with us that we don't know contain these compounds can contaminate our samples and lead to positive bias. So we have to be really careful. We don't wear Gore-Tex, which is actually really hard to find performance gear that doesn't have these PFAS compounds in them. So it's a challenge, and we have to be extremely, extremely careful. And wearing lab gloves over your mittens, also pretty exciting. Okay, so what we end up with are 15-meter ice cores. That's about the limit of what we can do in this type of sampling campaign. We're limited by the technology and what we can actually bring in on the plane. So 15 meters is about what we can do. So we end up with these 15 segments of our 15 1-meter segments that we bring back to our lab. And living on the ice cap is glorious accommodations of these little tents, which are in theory all season, but not really that warm. So we try to limit the time we spend up there. It's obviously a very hazardous environment. We have to worry about extreme cold. We have to worry about isolation. We have to worry about polar bears. It's a really intense experience, and so we try to get in there, collect ice cores, and get out as fast as we can. And we also, of course, have to worry about, this is the glaciologist look. The frostbite, windburn, sunburn. It's high elevation. It feels cold, but the sun is actually really quite intense. So I think she doesn't bother her, but some others does. Okay, so we collected our samples. Now what are we going to do? The first step is to make sure they get back to our lab without any issues. So we have to keep them frozen. Otherwise, we lose the integrity of the layers. So we keep them frozen. They come back on the Twin Otter plane, on the jet. They end up at the Toronto airport, and we collect them and drive really fast to Burlington, which is where we keep them in the freezer. So we don't want them to thaw at all. And the sectioning, we have to, again, be very careful. So this is Heidi. She was a master's student with me when I was at Memorial University, and she did a lot of the work I'm going to be talking about today. And the first thing she ended up doing was sectioning ice cores in a freezer, which she doesn't look too happy there. Yeah. So we were in a freezer at Environment Canada, sectioning these ice cores. We needed a clean environment to try and section them. So we have to work as cleanly as possible. So we wash all of our fancy ice core sectioning tools with solvent. We wear gloves. We don't bring in any Gore-Tex, et cetera, et cetera. And basically what we're doing is we're taking the ice core and sectioning it into bits that we can fit into our sample containers. So we take those sample containers, we put them in the freezer until we're ready to analyze them. So this analysis part, it's one slide, but this is really the hardest bit. So we take our samples, we thaw them, we then extract them. So the concentrations we find in the Arctic are very, very low. And we need to concentrate them, and we also need to clean them up. So we do a process called solid phase extraction, which selectively concentrates the compounds that we're interested in and lets the stuff we're not interested in wash away, essentially. And this is, of course, this has to be done in a clean lab, blah, blah, blah. So it's a pretty involved process. And we analyze these samples using the state of the science technique, which is liquid chromatography tandem mass spectrometry. And we end up getting a chromatogram that, well, probably not as nice as this, and essentially where each one of these peaks is related to the concentration of the different pollutants that we're looking to measure. Okay, so the first thing we really need to know before we can answer any of our questions is how old is the ice? So here we have this is actually a really beautiful ice core, this isn't mine, but we need to figure out what layer corresponds to what age. And so this is a pretty involved process. There are some different markers we can use, things that we know vary seasonally, so that are lower when it's colder and higher when it's warmer. And we can measure these, and as they vary over time, they can give us a really accurate idea of how old the ice is. So by doing this, we figured out that the one ice core we had, the oldest ice was 1977, and we collected it in 2015, so that was 38 years total of deposition. Okay, so now we end up with data. So I'm going to show you a few graphs. They're all going to be kind of the same format. They're going to look like this. So we have amounts of our pollutants as a function of depth, and we also have that as a function of time. So older, we're going from older to newer here. And we represent this data as a deposition flux. So what that means is how much was deposited in terms of a mass per unit area in a year. So it's an annual flux, and so these little bars are annual fluxes, and then we represent a moving average. And part of the reason for that is because we may not be as accurate as we thought when we're doing our dating, and we also can have melting that can impact our analysis. Okay, so we're going to look at 3 test cases to see if we can understand a little bit more how pollutants are transported to the Arctic. The first one is a production change of the perfluoroalkyl substances, and then we'll look at 2 regulatory changes, one for the flame retardants and one for the perfluoroalkyl substances. So the first one is actually a phase out. It was a voluntary phase out by the company ThreeM, famous for Post-it notes and other things. So what ThreeM made was a precursor that looked like this, and it was used to make all kinds of different stuff. So things like the Scotchgard major component and the stuff that we'd put on popcorn bags and blah, blah, blah. So this was really the precursor that was used to make a bunch of stuff. So this thing I'm calling commercial product 1 is a volatile compound that was used in like the Scotchgard and paper coating applications. And we have commercial product 2, commercial product 2, which is a non-volatile species. So we would expect that one to move through the ocean, this one to move through the air. Now the trick to this is that this compound can actually degrade into this compound in the environment. So that adds a complicating factor and one of the things we want to try to understand. So we expect that if this is being emitted and moving through the environment, it's going to happen pretty slowly through the oceans on the order of decades. If this is being released into the environment and being transported, it's going to go through the air. It's going to be faster on the order of days to weeks. And if this is the source of this, then we expect the response to be fast. So what happened in the late 1990s, early 2000s, was that there was a lot of, this was when we first started learning about these perfluoroalkyl substances. And one of the first places they were measured was polar bears. And the reason is that they're apex predators on this long food web in the Arctic. And what they actually discovered was this commercial product 2 was the single greatest contaminant in polar bears. So this made the news, it was a big deal, and ThreeM was pretty concerned about this. And what they decided to do was actually to phase out this chemistry altogether in 2001. So they started reformulating all of their commercial products. Now they use completely different chemistry to make these commercial products that ostensibly have the same properties, commercial properties anyway. Okay, so if we look at commercial product 1, remember this is the one that we expect to travel through the air and respond quickly. And what we see is, my animations aren't really working, but what we see is that this is the flux of that commercial product 1 here in the blue and the blue line, and then this is the reported production by ThreeM. So what we're seeing is that, yes, it was increasing in the 1990s, and then we see a decrease to almost nothing after the phase out of ThreeM. So this tells us that ThreeM's phase out was effective at reducing long-range transport of this commercial product to the Arctic, and that we actually understand what's happening here. So our hypothesis about how this compound was arriving in the Arctic is probably correct. Okay, so now we have commercial product number 2. This is the water-soluble one. And what we're seeing here is nothing like what we expected. We thought we'd made a mistake. We went and analyzed this a bunch more times to make sure that there wasn't an issue. So when we see the phase out here in 2000, we don't see much at all happening. And then we see an anomalous spike here in 2012. So this doesn't fit either of our hypotheses really. We don't see an increase that corresponds to decades after the compound was introduced to the environment, and we also don't see a fast response, which would indicate it was being formed from commercial product number 1. So we don't really understand what's happening at all here. The phase out was ineffective at reducing the long-range transport of this compound to the Arctic, and we definitely need to understand this more. So I'll come back to that in a little bit. Okay, so the next thing I'm going to talk about is regulatory change. So flame retardants have been around for a really, really long time. And before there were OPEs, there were PBDEs. So these are the polybrominated diphenyl ethers. They look something like this. And we found out they were really toxic, surprise, surprise. And they, because of this toxicity, they were being phased out. They are now completely banned. But while they were being phased out, in order to still comply with the regulations in California, replacements needed to be introduced. And if you guessed that the OPEs were the replacements, you are right. So these are the replacement compounds for these toxic, bioaccumulative, et cetera, PBDEs. So we've now replaced something that we know is bad with something that may be bad. And this is an issue where it's a cautionary tale. A lot of people I know are really concerned about their exposure to endocrine disruptors and things like that. So during the phase out of these PBDEs, people who were really aware of chemical contaminants were saying, well, I want to have my furniture and my electronics to be PBDE free. And sure, IKEA was one of the companies that was going around saying, like, yeah, we don't use PBDEs, we're great. But what they were using was these. So yes, you were not being exposed to these, but you were getting these. So advertising something as PBDE free doesn't mean flame retardant free, it means different contaminant present. Okay, so in our I Score, we are measuring these OPEs, these sort of second generation flame retardants. And what we see is not much happening in the late 70s, early 80s. And as soon as they started using OPEs as replacements for PBDEs, we see it starting to increase and then increasing continuously until about the present. So this is consistent with what we understand about production of flame retardants, and it suggests that we understand the production and impacts of these types of compounds on long-range transport and the Arctic. Okay, so the last regulation I'm going to tell you about today is the FOA Stewardship Program. So FOA is one of the PFASs. This is one that a lot of people have actually heard of, and I'll show you why in a moment. So this was something that was put together by the United States Environmental Protection Agency and Environment and Climate Change Canada. And they were working with the manufacturers of these compounds to reduce the emissions, essentially, into the environment. So for each of these manufacturers in North America, they took a look at their emissions in 2000, and they said, by 2010, we will have reduced them by 95%, and by 2015, we will have reduced them by 100%. So that's great. A lot of the companies they say they've been meeting their targets. But of course, we don't always trust the companies, so we have to go and measure. But you may have you may be familiar with this if you look carefully at when you buy your kitchenware. So I went over to Bed Bath & Beyond last week to see if I could figure out if I could even buy a nonstick pan with Teflon in it anymore. And the answer seems to be no. So you'll notice this is PTFE and PFOA free. This one also claims to be PTFE and PFOA free. So this is cookware, and we're also seeing now, I took this photo at the outdoors store REI in the US. So there are now, there's a push, a public push to produce these same types of performance products without the use of PFASs. So although we might say, oh, it's so great that the companies are voluntarily withdrawing these products, they actually are experiencing a lot of public pressure to do so. And again, PFOA free doesn't necessarily mean PFAS free. Okay, so if we look at our I Score for PFOA, what we're seeing is, well, not a lot. And if we take a look at the reference years, so we should be seeing a decrease from year 2000 down to 2015, which is not what we see at all. So the companies were really excited to see the decrease, and so they were very sad about this data, that the regulation and all the work that they've done hasn't actually been effective at reducing the long-range transport of these compounds and reducing the Arctic contamination. So what have we learned? Well, we know that some of our ideas about long-range transport are correct and some are not, and that these I Scores can actually tell us a lot about long-range transport mechanisms. So some of our ideas are wrong. And one of the ways we started thinking about this is in terms of who is actually doing the production and who is doing the regulation. So the two stories I told you about where compounds were phased out, both of those are North American stories. So ThreeM was the major producer. They phased out these compounds, and then there was a market gap. And so someone else started making them. And we really don't have a lot of information about chemical production that happens in certain countries, whether the companies aren't required to report their production to the government or whether the government doesn't report that production to the public. Either way, we don't know what companies are producing and emitting into the environment. So we know that after ThreeM phased out those chemicals, that production really started ramping up in China. And we know that our Canadian Arctic, is influenced by North American emissions, but also emissions from Asia and Europe. So even though what we're seeing in North America is a move away from some of these compounds that doesn't actually prevent the contamination of some of our most vulnerable ecosystems. And one thing I wanted to also point out here is that these I Scores are very valuable, but they're a diminishing resource. So a lot of the ice caps that we work at, we've seen dramatic increase in melting since about 1995 or 2000, depending on the I Score. And so that can really inhibit, it changes, or compromises the integrity of the temporal trend, and it basically makes them not useful for recording this type of deposition. So it's yet another reason why preventing temperature increase in the Arctic is very, very important. Okay, so what are we doing next? So obviously, I haven't answered all the questions. Some of the things we obviously we were right. Some things we were not right. So we have some new samples. This year, we collected at the Oxford ice cap. And that ice cap is located on Ellesmere Island, just south of Alert. And one of the reasons we want to look at different ice caps and collect ice cores from different locations is because we might expect some spatial variability. So this more northern ice cap is likely to have more influence from Asian and Europe emissions. And also, we are limited to 15 meters logistically, and different ice caps have different levels of deposition. So whereas in the Devon ice cap, we could get about 40 years of deposition, on the Oxford ice cap, we think we should get 50 to 60 years of deposition. So this hopefully would allow us to go back before these chemicals were being produced at all, and actually see a clean environment. We also are hoping to look at other pollutants of concern. So of course, when companies replace their chemistry with new things, they don't tell us what it is. So we have to go and find out. So we've been archiving these ice cores so that we can go back when we find out that there are other contaminants of concern. We can go and look and see if we see these in our ice cores, and we can look at the temporal trends before having to go out and do another sampling campaign. Now, each one of these sampling campaigns costs about $60,000. That's why we don't take it lightly doing this. And we're also doing some lab experiments. So when these field measurements really inform us, and they tell us what we don't understand, and without spending $60,000, we can do some experiments in the lab that can really inform us. So one of the great facilities we have here at York is an environmental reaction chamber. And this chamber is essentially, it's a Teflon bag with lights around it, and we can systematically vary the composition inside this bag to mimic different environmental conditions and better understand how compounds might move through the atmosphere. And okay, that's all I have for you today. Please feel free to contact me at my email address, or if you want to learn more, that's my website, and thank you for your attention.